In our earlier tape on pilot protection, we took a brief look at the basics of power line carrier. Now, in that particular tape, we were more concerned about what PLC can do for us than how it does it. Now, in this videotape, we're going to examine PLC equipment in more detail. First, let's go into the switchyard and look at the line hardware. This piece of equipment, which is connected in series with the line, is called a line trap or wave trap. The line trap may be mounted vertically or horizontally, like this. The simplest type consists of a large coil, that is, an inductor, made of conductor material and capable of carrying high load current. It must also be able to withstand very high values of fault current for short periods of time. As you already know, the objective of the line trap is to confine the injected carrier signal to the desired conducting path. That is, the transmission line between transmitter and receiver. The line trap or inductor is sized so as to provide a reasonably high impedance to the carrier signal, which may be transmitted within the frequency range of 30 kilohertz to 500 kilohertz. At the same time, the inductor must offer zero or very low impedance to the flow of 60 hertz power current, which may be, say, 800 amps at 230 kilovolts. The value of inductor chosen is usually quite small, about 2 millihenries. You will remember that inductive reactance is calculated from the formula XL equals 2 pi FL, so it is proportional to frequency. At 60 hertz, a 2 millihenry inductor will produce an inductive reactance, that is impedance, of approximately 0.75 ohms. However, at the carrier frequency of, say, 100 kilohertz, the impedance of this inductor will be relatively high, about 1,250 ohms. So the loss of carrier signal will be quite small. We can draw a chart showing impedance against frequency. You can see that this simple, untuned line inductor does offer a reasonably high impedance over a wide range of carrier frequencies. However, experience has shown that in certain installations, the inductance can create a high-frequency series resonance with capacitive circuits on the bus side, such as CCVTs, lines, transformer windings, and breaker bushings. The consequence of this is a drastic reduction in impedance and loss of carrier signal. Many line traps consist of a tuned resonant circuit with inductance and capacitance in parallel. I'm sure you all remember this circuit from basic electricity. The value of inductive reactance is chosen to be exactly the same as that of the capacitive reactance at the desired resonant frequency. If we apply a voltage across this parallel circuit, we find that the current flow in the supply lead is practically zero. This is because within the resonant circuit, current is flowing from the inductor to charge the capacitor, and then in the next half cycle, it is discharging from the capacitor back to the inductor. The resonant current oscillates continuously between inductance and capacitance. If the circuit contained absolutely no resistance at all, the current supplied from the source would be zero. As no current flows in or out of this theoretical circuit, it provides an infinite impedance to the flow of current. In practice, resistance does always exist, but the circuit still provides a high impedance at the tuned frequency. Let's look at a typical case. The value of the inductor here is 0.2 millihenries. You can already see an advantage. This is 1/10 of the value of the line inductor that we previously examined. This gives us the very low impedance of 0.075 ohms at 60 hertz, and so reduces associated losses due to flow of power line current. At a selected carrier frequency of, say, 100 kilohertz, the inductive reactance will be 125.3 ohms. So in order to provide resonance, we need to select the size of our capacitor so that it will produce a capacitive reactance of 125.3 ohms at a frequency of 100 kilohertz. We can calculate this from the formula. The capacitive reactance, XC in ohms, equals 1 over 2 pi the frequency in hertz times the capacitance in farads. This works out to a required capacitance of 0.0127 microfarads. But what is the effect of this capacitor at power system frequency? Well, at 60 hertz, the capacitive reactance will be equal to about 200,000 ohms. So we see that virtually all of the 60 hertz current will flow through the inductor, which has only 0.075 ohms. And what is the impedance of this combined resonant circuit at 100 kilohertz, the carrier frequency? Well, if we had a perfect resonance, that is the theoretical condition with zero resistance in the conductors, then this circuit would provide infinite impedance. But the circuit does contain resistance, and in practice, the impedance to 100 kilohertz current will typically be around 5,000 ohms. If we plot the impedance against frequency, the curve looks like this. The value of impedance falls off sharply as frequency moves away from the designed resonant frequency. At the resonant frequency, the inductive and capacitive reactances cancel out, so that the characteristic is that of a resistance. However, as soon as the frequency is changed, as is often the case in carrier operation, the perfect parallel resonance of the wave trap will be disturbed, and it will become inductive or capacitive. From this curve, we can see that a small frequency change from 100 to 98 kilohertz will produce a highly inductive component with the consequent potential for series resonance with bus equipment. In order to avoid this potential problem, further resistance is added to the line trap. This actually has the effect of reducing the impedance at the resonant frequency, but improves the off-frequency operation by providing a resistive characteristic.